Welcome, everyone. For some reason, people are afraid sitting next to me. Please report to Erwin. Yeah, it's usually reserved for Sean, but people wait to and so we just had an excellent ITC colloquium by Kathryn Johnston, who is sitting over there. And she will speak in a little while about something related, but not the same. We'll also have a CFA colloquium today by Marla Geha in a related area, field. And Marla will be the first speaker, actually, and you can see her title over there, A Search for Stellar Mass Black Holes via Optical Variability, something completely different. She's not very far from here, Yale, although we would like to see her more often. The second speaker will be Emeline Bolmont. Is she here? Oh, over there. And she will talk about habitability around cool dwarfs. That'll be refreshing to hear again about exoplanets. We have heard too much about the gravitational wave astrophysics recently. Then we'll hear from Kathryn Johnston about physical manifestations of chaos and regularity around galaxies. And finally, we'll hear from Jermyn from the Institute of Astronomy at the University of Cambridge. Where is Adam? Over there. He's graduating, and he will talk about the mixer numerical perturbation theory for turbulence. Marla.
Thanks. So it's a pleasure to talk to you now, and it will be a pleasure to talk this afternoon. I typically talk, and I will be talking this afternoon, about Milky Way satellites, Milky Way dwarf galaxies, and the project I'll talk about this afternoon is understanding our Milky Way in a more cosmological context, so understanding Milky Way analogs in the local universe, and very much in the spirit of talking about something completely different for lunch today. This is a project that I started because I was teaching Astro 101, and I have convinced my former TA, who is now perhaps going to do this as his PhD thesis, to take up this idea. So I was teaching Astro 101, and I was talking about black holes, and specifically stellar mass black holes, and it just kind of dawned on me that, assuming we have, knowing the stellar populations in the Milky Way and some normal IMF, there should be something like 1 million or more stellar mass black holes in our Milky Way alone, and we know at least dynamically confirmed of only 18, and this sort of just pissed me off. And so I was walking. I had an idea of how you might find black holes otherwise, and I was walking with my TA, Michael Warner, and I mentioned this, and he sort of decided to pick up the idea and run with it. And over the summer, we've had some success, and we'll hopefully test our idea in the spring. And so I very much look forward to input on this idea. I am a complete novice in terms of black holes and black hole binaries, and so this is very fun for me because I feel like a graduate student, and I feel no shame asking really dumb questions about this idea. So we know of only 18 dynamically confirmed stellar mass black holes in our Milky Way, at least. All of these have been found via X-rays. That is, these are not only black holes, not only are they black holes in binary systems, they're black holes in binary systems that are fairly close. There's been mass transfer, and those have all been found via X-rays. And of course, the motivation for this is manyfold. So the LIGO sources are obviously very much a motivation for finding more stellar mass black holes in the Milky Way. The mass ranges seem to be a little bit different and interesting. I come at this because I'm interested in knowing the more general population of black holes in our Milky Way from a chemical evolution point of view, because all these things had to have formed in presumably in supernova, which produces many of our chemical elements. So there are many, many reasons why we want to expand the number of stellar mass black holes in the Milky Way. All of these objects, these 18 that are known, were discovered in the X-rays. However, you can see variability in the optical for these systems. And so these systems, because they're fairly close to each other, the black hole and the star are fairly near each other. The luminous star is not completely spherical. It's overflown its Roshlov, and so it has some non-sphericity, and so this gives rise to ellipsoidal variations. And so the base of this optical light curve is ellipsoidal variations, where you're just viewing the luminous star from various different vantage points. And the periods of these objects are sort of hours to days. And then on top of that base light curve, when the object is mass transferring and there's X-ray variability, there's some extra variability that you also see in the optical. However, these black hole systems all have some periods of X-ray quiescence where they're not super X-ray bright. However, none of these objects were discovered in quiescence. And so the goal of this work, or the goal of this project, is to search for black holes that are in close binaries, but which are not X-ray bright, using their optical variability. And so really just take a baby step towards understanding the population of black holes in our Milky Way by taking one step away from the known objects so far. And so the question is there something unique in the optical light curve of these black hole systems that differentiates itself from, let's say, stellar mass black holes? And so here, what we've done over the summer is simulate a whole bunch of black hole binary systems and stellar binary systems, looking at the light curves and just asking this question: is there something characteristic that is different from a black hole secondary to a luminous secondary? And so here is a system that is going to be our major contaminants. These are algal type variables, where you have you do have an object that's overflowing its Roshev with another smaller secondary, and you can see the light curves of these two simulated objects are actually quite similar. And so I am sufficiently naive to ask the question: is there anything that's different from these two types of systems? I think people who are experts in this would say, no, why are you wasting your time? But I don't know that. And so we have been fitting these light curves using Fourier series, and to first order, sort of the first couple of Fourier terms, the answer is no. There really are no differences that we can find between black hole secondaries and luminous secondaries. But as you go to higher order Fourier terms, we have found a unique part of parameter space that we can only simulate, we can only habit by black hole systems. And so we believe that there is some characteristic shape of a particular type of configuration where we can find black holes. And so our answer right now is yes, maybe. And so we have now used that technique to search every variability catalog we can come across. And so I came at this project because I was many years ago part of the Macho team, where we have this beautiful light curve database that's been very much underused, in my opinion. And so we've searched through a whole bunch of various different variability catalogs. We're still going to search a whole bunch more. And we now have scheduled radial velocity follow-up this spring in a couple of months. And so we're going to take our candidates, go and get multiple radial velocities across the full phase period. We're going to require at least 5 radial velocities in order to actually measure and understand the nature of these objects. Perhaps we'll find something. Perhaps we'll realize that there's more contaminants in this space and iterate across our method. But I'm actually quite excited about this. And I really do welcome suggestions. This is very much a new, fun project for me. And so I am still reading the literature and continue to be surprised that nobody has done this yet. So if I am wrong, I'd love to know that. We are parametrizing our light curves in one particular way using Fourier series, but there's, I'm sure, better and perhaps alternative ways to do that. We're also very interested in other light curve variability surveys out there to try and increase the number of candidates that we have access to. And so I will stop there. I was talking to Josh Grinley today. He was telling me about that source. Yeah. Fabulous. No, I'm hoping to get lots of sources. My interest is not just one. I want to start to understand the populations. But he told me about that source. It sounded interesting, although not definitive. And so I didn't realize there was a colloquium recorded.
But then in the near future, let's say within a couple of years, to look at diabetes.
Absolutely. Yeah, and there was 2 papers recently that were just published about predicting what Gaia will see. This is sort of complementary, similar but complementary. So I think there's a lot. Yep, there's a lot that will happen in the next couple of years in this field.
Have you tried phasing the color information variability?
It's a good question. So color is something we haven't folded in, but we think will actually be very useful. And the reason we haven't thought about color is because the Palomar Quest is our main survey that we've been targeting off of, and they don't have color information. But there are other ones that certainly do, and I think that may end up being really important.
Most modern variability surveys do survey.
Yep, I agree with that.
Okay, so there must be a specific.
Oh, sorry, I didn't realize I'm not allowed to.
Have you considered what the variability might be in the near infrared as opposed to the optical?
I have not, only in the sense that there's a lot more optical public data out there for variability, but I would be happy to search in the infrared as well.
Are you using any light curve synthesis codes to model the light curves, or just the Fourier series?
Yeah, so we're to synthesize the light curves, we're using ELC, which is one of the major ones. We've been looking at Phoebe as well. And I'd love to talk more about that, because I think the key here is we do think there's a region where black holes are unique. But that completely depends on the models and how the models are doing. So I want to use multiple models to try and see whether or not what our contaminants will be.
So there must be a specific range of binary separations where you can detect this and the black hole's not X-ray.
Exactly.
So out of 1 million black holes, are there predictions for how many are in binaries of this separation?
It's a good question. The predictions will be all over the place, and this is sort of to constrain that. It's going to be a small number. So again, this is just a baby step towards the full population.
Another question over there.
What are the periods and magnitude ranges of the sources that you've found so far?
Yeah, so the periods, we're sort of explicitly looking in sort of hours to a few days, just to model, that's what the ones that are known so far. So we're really just looking at, for analogs of the ones that are known so far. And the magnitudes, we can choose at the moment, because we're just taking the cream off, we're looking at bright things. So 17 to 14th magnitude is sort of the range we're going to look at and target in the spring.
There's lots of planetary searches, transit searches out there that have light curves.
Absolutely. So Kepler is one of the things that we are searching for to pick up more candidates.
Any other questions? No, that's
Okay. Can you hear me? Yes. Okay, so thank you for having me here today. So I'm Emeline Bolmont. I'm a postdoc in the CEA in France, and I've been visiting the CFA for this week. And I will tell you about a part of my work which evolves around the habitability around cool stars. So I've been working on dynamics, tidal dynamics, and also a bit on climates. So I'm going to try to tell you all about that. So just to be sure that we are talking about the same things, here when I talk about ultra-cool dwarfs, it's very low mass stars and brown dwarfs. So anything with a spectral type later than M6. So knowing that, what we are looking for, basically when you are talking about habitability, of course, is to find like the closest planets to Earth. So basically you need a small rocky planet. You need it in the habitable zone around the Sun-like star. So the habitable zone is the region around the star where if you have a planet with the right atmosphere, you can potentially have surface liquid water. But of course, that is not sufficient in a sense that usually with the methods that we have now, we have, okay, the mass, the radius, maybe both of them at the same time if you're lucky enough. But what you really want to know also about these planets is a sense of what's the atmospheric composition. So you need to somehow be able to do other type of observations to try to constrain that. And so to put it into context, here you have the orbital period of known exoplanets today with respect to the mass of the host star. So you have the solar system planet here, some of them at least. The first one ever detected is 51 Peg, as you might know, in 95. It was a hot Jupiter around a Sun-like star, so it was nothing near close to habitable. But we have been doing some progress about that, and it was looking at around less massive stars. So, for example, the first rocky planet inside the habitable zone of a star was Kepler 186f. It's about 50% the mass of the Sun. More recently, there was LHS 1140b, which is like around a star of 13% the mass of the Sun. Then Proxima b, 12% the mass of the Sun. And very recently also the planets of TRAPPIST-1, where here it's like 9–10% the mass of the Sun. So very, very low mass stars, and all these stars have planets inside the habitable zone. And for example, for TRAPPIST, it's like 3 of them might be in the habitable zone. So why are we looking at these low mass stars? There are several reasons. The first one is that the low mass stars are very numerous around us. It's like 75% of objects around us are very low mass stars. The planets around this kind of objects are much easier to detect. For example, the transit depth is going to be much deeper for this system here than an Earth around the Sun-like star. And last but not least, these planets in the habitable zone of the very low mass stars are the only planet of the habitable zone that we are going to be able to probe the atmosphere in the near future. And that's maybe the best point of them. So, for example, it has been shown with these two instruments, so SPHERE and ESPRESSO at the VLT, that if you look at Proxima b for some time, it's possible to detect dioxygen or water with these two facilities. There is also, of course, the EALT, so it's for 2025, maybe even later than that. And with that, you can also have a reflection spectrum for Proxima b, potentially, with possible detection of water. And of course, as you might know, there is also the James Webb Space Telescope, which is going to do transit spectroscopy. So, for example, here it's for TRAPPIST-1c, I think. And they show that if you have like 60 transits with the James Webb, you can detect ozone feature. So it's really exciting because we are really touching, in the very near future, the atmospheric composition of habitable zone planets, which is very nice. But of course, when we're going to have chemical signatures from these atmospheres, we might think, okay, maybe some of them are due to life, but of course you have an infinite number of processes that can also create one given chemical signature. For example, you can have volcanism that's going to inject in the atmosphere some gases and any other thing that you can think of. And I would like to illustrate this with the example of oxygen and ozone. So as you know, on Earth, we have dioxygen in our atmosphere, and it's due to the life processes. But what would happen if you consider a planet around a dwarf? If you observe dioxygen or ozone, would it mean that you have life? And in order to answer this question, you really have to study how the system evolves from its formation basically to today. And the thing is, actually, these low mass stars, and here it's the example of the brown dwarf, but the principle is the same, is that they evolve on gigayear time scales. So you have the radius, the spin, and the luminosity that evolves with time. So this has consequences on the tidal dynamics of the system, and of course on the insolation history of the planet. So for example, here you have distance as a function of age, with the habitable zone that's coming closer as the star becomes fainter and fainter. And if you look at the evolution of one Earth mass planet around this kind of object, this is the kind of thing that you get. So here, for example, the first one experiences tidal migration. I'm not going to go into detail for that. The important thing is that before reaching the habitable zone, they are in a region where it's too hot to have surface liquid water. So all the water is in the atmosphere. It's the runaway greenhouse state. And the thing is that during these periods, so when the planet is interior to the habitable zone, so all the water is in the atmosphere and submitted to the high energy radiation from the star, which can drive atmospheric escape. So in the end, when the habitable zone arrives where the planet is, you can consider that all the water was stripped away, and so you would have a kind of Venus-like planet inside the habitable zone. So it would not be habitable in the sense that you wouldn't have liquid water because all the water is gone. But if you're lucky enough, you were able to retain some of the water initially provided during the formation processes. And then when the planet arrives in the habitable zone, then the water can condense and you have lakes, oceans, what you want. So there were some studies about that in 2013 and 15 for brown dwarfs and M dwarfs that showed that it would be more the first case, in meaning that the planets should be desiccated by the time they arrive in the habitable zone. So we decided to revisit these studies in 2017, and what we did is that we used more recent observation about the high energy radiations from this kind of dwarfs, and we also used a slightly improved model using radiation hydrosimulations from Owen and Alvarez. So the principle is the following. So you have all the water in a gaseous form in your atmosphere. First, you have FUV radiation that's going to break your water molecules. Second, you're going to have XUV radiation that's going to heat up the exosphere and drive the atmospheric escape from hydrogen and oxygen. And then, once the planet arrives in the habitable zone, then you can recombine your molecules, and because you're in the habitable zone and the temperature is okay for that, then the water can condense. So at the end, you have less water, obviously, but also, as you can see, you have a dioxygen excess that is going to appear naturally from this phenomenon. So we applied that to Proxima b. We also did it for the planets of TRAPPIST-1, but I'm just going to talk about that today. So for Proxima b, what we found is that by the time the planet arrives in the habitable zone, so after something like 0.1 gig a year or so, it lost less than 2 Earth oceans. So you might think it's big, 2 Earth oceans, but actually during the formation processes, you can very well form planets with huge amounts of water. So for us, 2 Earth oceans, it was not that much. So we thought that, okay, Proxima b could still have water. And this water loss is accompanied by the oxygen buildup. And you can see that you can have up to, you can build up in the atmosphere something like 100 bar of dioxygen via this process. So in the end, observing dioxygen or ozone inside on the atmosphere of a planet around a dwarf might not mean that you found a trace of life, but rather that the planet experienced hydrogen loss and water loss. So to conclude, I wanted to do try to do a list of all the pros and cons about habitability around these objects. So the pros is that, okay, there are a lot of dwarfs, the planets are easy to detect. On the con parts, the low mass stars are very active, so as I showed you, you can have water losses. I showed you from the hydrodynamical point of view, but you can have also losses due to the stellar winds, for example, that would add up to what I showed you. And there are diverse things that can be dangerous to life around them. But then you also need a bit of activity, because it has been shown that UV might be actually quite important for the appearance of life. So I guess you have to find a balance somehow. But if you don't really want too active bodies, brown dwarfs are supposed to be less active. And then you have more dynamical things. For example, as the planets are very close to the star, they are going to be synchronous. So they can be problematic for the habitability, in the sense that you can have a cold trap on the night side. But then there was this study by Martin Turbet in 2017 that showed that planets in the habitable zone of these low mass stars actually, there is a wide variety of atmosphere conditions for which you can find liquid water at the surface. So it was a nice result. Then on the cons, the fact that the biosignatures are not quite reliable. But anyway, even if it's not reliable, we are going to learn a lot of things with the atmospheric characterization that we will have with the James Webb and the EELT and so on. So thank you. I'm sorry if I spoke a bit too much. I see. Not that much. The first reason why is that on the observational point of view of the matter, for example, for the planets of TRAPPIST-1, we have found that some of them are quite with a low density, which would mean that they have a lot of volatiles, so potentially an atmosphere, I guess. So I suppose that it's not that bad. And yeah, sure. Yeah.
It's not clear how much of a wind these things even have. I mean, especially if we talk about the brown dwarfs. I mean, Jupiter doesn't have a wind. These things have extremely short rotation periods, so they're not spinning that. I'm talking about stars. I mean,
for the low mass stars, yeah.
For the eminence or so, they seem to be more similar to the brown dwarfs than the higher mass stars.
But anyway, that's something that we are going to be able to test because, for example, Proxima b, I think it has been shown that it's quite active. So if we find via, phase curve measurements, so on, that the planet has an atmosphere, I guess it will tell us a lot about the capacity of these objects to actually survive very strong environments. So even if we don't have the answer on the theoretical point of view, I'm sure that the observation will tell us something about that. Yeah, that's a good point.
So I was happy to see that you're using the activity measurements from the work that Peter and I have been doing. But most of that work is based on nearby sources that are probably significantly older than the phases you want to consider. So are you scaling up the activity as a function of?
Yes. Okay. Yeah. Actually, usually we do both. We consider like constant luminosity and X. But we also consider like it's that the ratio Lx over L bolometric is constant. So we have stellar evolution models for this kind of low mass stars, and so we scale the X luminosity to the bolometric luminosity that evolves with time. So we do that, yeah.
Usually I hear that it's not just either molecular oxygen or ozone, but the combination of one or both of those and methane that gives one high confidence that there could be a biological origin to those gases. Is that something that your analysis would agree with?
Well, I don't know if my analysis would, but I completely agree with you. And I think that it's not going to be one detection of one particular chemical element that's going to tell us that, okay, there is life. It's going to be probably a succession of things that are not quite right, saying, okay, we can't explain that with what we know. But I guess that it's not for the near future at this stage, I think. But anyway, if we have a planet with a detection of ozone, or even methane, it would be super exciting. Because methane, it's not really my field, but I think it gets destroyed very easily. So to explain the methane in an atmosphere, you have to have something that pumps methane into the atmosphere quite regularly. So Could it be life? Could it be volcanism? I don't know. And actually, the planets, for example, the best example for me is TRAPPIST-1 because I also work on n-body simulations with tides and so on. And so when you have a system like that with strong planet-planet interactions, you have an excitation of the eccentricity of the obliquities of the planet, and you can have tidal heating that can be quite important. For example, for the TRAPPIST-1b planet, we evaluate the tidal heating to be like even bigger than Io. So we would expect, for example, this planet to be very volcanic with a lot of activity. And all the other planets also experience this kind of tidal heating from the inside. So we expect that it's going to have an impact on the atmosphere somehow. But I guess we would have to work with geologists in order to try to constrain this kind of input in the atmosphere. It's really not something I'm capable of doing. Yeah, that would be the easiest, actually. I was going away with the microphone.
Okay, physical manifestations of chaos and regularity around galaxies. This talk is growing out of work where we're looking at the destruction of satellite galaxies around the Milky Way. And for the second time today, here's an image a visualization that Anna Benacha made of the Sloan Digital Sky Survey. And in this image, stars in the Sloan Digital Sky Survey. And in this image, you can see beautiful streams of stars from dead and dying satellites. And we got set off on this particular study by looking at the beautiful stream of stars that was originally found in Sloan coming from the Palomar 5 globular cluster. We performed a pretty basic experiment. We were running simulations. This is work led by Sarah Pearson, of the destruction of a globular cluster to try and mimic the tails from Palomar 5. And this is just showing you our basic result. In the background is the Palomar 5 data realized as contours. And on top, you can see the points from the simulations. And in a basic oblate potential, which contained a disk model and a spherical halo, we found we could easily, trivially find matches to the data. However, in one particular model where where we took a triaxial model for the Milky Way's dark matter halo, also a disk, and the triaxial model was motivated because that triaxial model had been shown to match the Sagittarius data for the dwarf Sagittarius, we found that we could not find a match to any orbit on which we could reproduce Palomar 5's tidal streams. They took on this rather disrupted appearance. And the exciting thing about this, twofold. First of all, this means we've ruled out that potential model with morphology alone of one stream. It's only one model, but still, it's kind of fun to be able to do that. And the second point is, why is this happening in this model? And the obvious culprit that we wanted to point to was dynamical chaos. However, what is really exciting about this, in my view, is that historically, or at least in conversations I'm aware of, people really don't talk about chaos as being important in this region of the galaxy. The galaxies, in general, are thought to be dominated by a fairly spherical dark matter halo. And moreover, the orbital time scales there are a gigayear or so. So they have dynamical ages of tens of gigayears. So you're expecting at most very madly chaotic orbits. And that chaos should not manifest itself in a way that you should be able to see in the lifetime of the universe, right? That's historically what our expectation is. So if we actually remind ourselves of what we mean by chaotic orbits, Regular orbits are ones in which you can find predictable paths, and they conserve some properties. So, for example, a regular orbit would conserve, you'd be able to identify 3 frequencies of oscillation of that orbit with a Fourier transform that remain the same throughout the orbit. A chaotic orbit, on the other hand, is one in which those orbital properties change, which means the path becomes unpredictable. And specifically, if we talk about frequencies, if you took a Fourier transform of one part of the path of a chaotic orbit versus another part, you would find the frequencies would drift. So one way of identifying chaos is to look for this drift in frequencies in numerical experiments. So Adrian Price-Wellen picked up this project with the questions that had been left over from Sarah's experiments, and he calculated a frequency drift time for the orbit that we'd found in this traxal potential. And he indeed found that the frequency drift time was actually many times the Hubble time, and therefore this orbit was not chaotic within a Hubble time in the traditional definitions. And so what Adrian then did was to ask, well, okay, so in general, if we take a mildly traxial halo, forget about the disk, just a mildly traxial dark matter halo consistent with n-body simulations of structure formation, what do we expect for streams formed in that halo on different orbits? And he chose 4 different orbits, 2 exactly regular. They all had the same energy. 2 were exactly regular. 1 exhibited weak chaos, meaning a chaotic drift timescale of 10 to the 5 gigayears, so 10,000 times the Hubble time. And the other one, strong chaos, but this is defined as 10 times the Hubble time. In other words, 100 gigayears. And if you look morphologically at what happens to streams on these timescales over the course of a Hubble time, along the regular orbits, the streams from globular cluster scale streams remain coherent, as you would expect. But even in the case of weak chaos, you see what we were dubbing stream fanning over the lifetime of the universe. So in other words, we're detecting mild chaos, which should take 100,000 gigayears to detect, which to be important. We're detecting this with tidal streams over a period of 10 gigayears or so. And if you look in frequency space, this is just plotting the frequency space for the same simulations. You can see this is a manifestation, a physical manifestation that we can observe of the frequencies of the stream members drifting over the lifetime of the universe. So of course, then the question is why? If we've calculated this frequency drift time, and it should be really long, and yet we're seeing a change on a much shorter timescale than we expect, why would that be? And in order to explain that, we can, the way we've explained this, I'm going to show you a cartoon of how we can look at orbit space. So if you look at orbits in a traxal potential, a traditional way of visualizing a single energy surface is to look at the ratios of frequencies. There are 3 frequencies, so you project it into 2 dimensions. The ratios of frequencies of those orbits, and they all have the same energy. And you can see that if the ratio of these frequencies are rational, then you'll have what is called a resonant orbit, where the orbits will actually close on themselves. And these will appear as straight lines. So in a globally integrable potential, any orbit in this space would just stay at the same place the whole time. Chaos will mean that the position in this plane would change over time, right? So as you make the potential non-integrable, in other words, it admits more chaotic orbits, what you find is that you still get lines of regular motion around the resonant orbits and close to the resonant orbits and near resonant orbits. And far from the resonant orbits, you can also get regular motion. But there's a layer of stochasticity between the regular resonant orbits and the regular non-resonant orbits, which lines up with the projection of those regular orbits onto this plane. And in particular, those chaotic regions become particularly large around intersections of the resonances. So what we actually think we're seeing is that when an irregular orbit, a chaotic orbit, moves in this space, if it's in this part of the diagram, it can move, it's a region of strong chaos, it can easily move. But even in the mild chaos regime, what we believe we're saying is that rather than the frequencies just drifting slowly over the Hubble time, there's a slow average mean drift, but there's large oscillations around that mean drift on a much shorter time scale. So what we actually think is happening here is in this weakly chaotic regime, there's large excursions in this stochastic layer, even though you get a long time scale for the mean drift of these frequencies to change. So this was our conclusion of why we're seeing this effect. But I think that what's more exciting to me about this project is not just this single conclusion, but the implications of what this means for studies of streams in this context. It's a new window, a new way we can use streams. Most exciting is this idea of being able to actually read stream morphologies in a way to understand very sensitively whether there are orbits in our galaxy that are chaotic. In other words, I would now say we can go back to the visualization that Anna made, and we can actually point to these streams here, Orphan, GD1, Palomar 5, and we can say, we would expect these streams, even on very madly chaotic orbits, not to be able to maintain their coherence. So the existence of these streams we're seeing here is like making a map of where chaos is not in the galaxy. These are regular orbits, extremely regular orbits. As another example, Adrian Price Whalen went on to study the Ophiuchus stream, which is a tiny stubby stream close to our galactic center, and he showed in his paper that you could actually attribute the stubbiness of this stream to the presence of chaos. This stream is orbiting close to the galactic bar, so it's interacting chaotically with the bar, and you can actually see that if you run a simulation of something on a similar orbit, you can see occurrences where you get short stubby streams because the ends of the streams have been disturbed by chaotic orbits. So in other words, we're finding out, this is what I mean by physical manifestations. We've gone from quite a theoretical concept of whether orbits are regular or chaotic to a way of actually identifying them around our own galaxy. And I just want to end, oh, great. I'll just say, there are a few things that that's brilliant. Okay, let me play this again. These are the things that I'm most excited about this. I really think this is a new regime for studying chaos. It's not over many, many orbital timescales. It's also new in that we're looking at physical space projections. It's also different in that we're not looking at structures of bound systems. We're talking about the consequences for unbound systems. And finally, there's many applications, not just to streams, but to any pair of stars that started associated, so down to binary stars, from large galaxies down to binary stars. If we can find those associations later, we can think about what chaos would have done to the evolution or not, and use it as a constraint in the end on potentials. Yeah, that's it. Thanks.
There is another problem for the parameter, which is the cloudiness of the halo. How would we distinguish between the chaotic behavior and just spreading the stars with cloudiness?
Yes, well, so that in effect, that's another type of chaos. You're right. So I think that we'll need to think about that question. But my brief answer would be, my intuition would be that there's chaos due to the mild traxiality, and I think that's going to cause effects such as stream fanning, whereas things like clumpiness are going to cause the streams to be chopped up more. So my hope is that those types of effects are going to be distinguishable. Yes, I have not done that, but that's exactly what we would hope to do. This potential measuring would be making frequency maps and seeing whether those streams in a given potential. So we have not done that. It's waiting to be done.
New work done here on the Ophiuchus stream shows it not to be quite stubby. Showing the original tape. This is where the studies are.
Yeah.
Whether it's spanning is still to be determined, but it's an ongoing project.
Yes.
It's
Yes.
about twice as long as what's shown in the original.
Well, so that's interesting. I mean, I'm aware of some of that work, and I should have mentioned it. I was standing here, I was like, damn it, I should have mentioned that work. But I know that I think Adrian's working with this team as well, right? And some of it is you're finding okay, you should talk about your own work. Associated stars. I mean, whether it's fanned or if you're showing, I would like to chat afterwards. If you show them it's long and thin, or just longer but still fanned. The hope is you would find things close in velocity, but morphologically not. As then. Okay, interesting.
So I'm going to play devil's advocate here for a minute. If you have one of these streams that's in a weakly chaotic regime, what percentage of the particles that you in your simulation would start in the stream end up scattered due to or on wildly different orbits due to chaos? Because I can understand if you have something like the Ophiuchus stream where there's a significant shortening of the stream due to resonant interactions with the bar. Like, that makes sense to me. But I find it very hard to see how you would then find stars that are on these chaotic orbits and associate them back to something in which most of the stars are on regular orbits. Do you have an idea of how that would work?
Yeah, well, I think that's exactly the experiment that it's being done here. You look for things that are close in velocity, and they shouldn't be in that region of space, but they're not part of a collimated stream. That's how you would run that experiment.
Why do the velocities have to be similar?
Because they came from the stream in the first place. So we're talking about a stream that's 2 kilometers per second thick, right? So if you find things locally that are within plus or minus 50 kilometers per second, but you're expecting none, then this is telling you something interesting. Right? So that's one experiment. But the other way this could be, this idea could be interesting is just looking at the frequencies of streams we see and seeing if that's consistent with the distribution of triaxialities in the infall distribution we expect around galaxies more generally. So I talked about the Milky Way, but the nice thing about this, another nice thing about this is that it's using morphologies alone. So it's very cheap. That's what I meant by cheap. It's very cheap to run this experiment, and we should be able to do this even for galaxies where we aren't able to get large samples of radial velocities in terms of frequencies statistically.
That's beautiful work. Thank you very much.
There we go. Okay. So I want to talk about Mixer, which is a new turbulent subgrid model that I've been developing with Chris Stout, Pierre, and Kumar. So the idea is that we have lots of scenarios, lots of very different scenarios in both stars and gaseous planets, where turbulence really plays a critical role. Right, so these are scenarios where you have shears or convection, differential rotation, magnetic effects. These are all cases where you really care about the turbulence, but you may not want to simulate it all in great detail. Right, you may want to follow it on evolutionary timescales rather than on dynamical timescales. So just to pick one specific example, you might have a convection cell. So here, material buoyantly rises and then falls. And a natural question to ask is, how fast is this material going up and down? Right, it's sort of a very basic question. And similarly, this transports heat. So how much heat does it transport, or what's the rate? Or even so, if you set it spinning, then the Coriolis force should start distorting these convection cells. And so then your heat transport is no longer parallel to the entropy gradient. It's now at some angle. And so you want to know what's the angle. Right, so all of these things are things that you'd like to be able to put into models of, evolutionary timescale models of stars and planets. So all of these effects are really sort of summarized by two quantities. There's the stress, which is R, and the diffusivity, which is D. And these are just expectation values of fluctuating quantities in in the fluid, right? So R is basically telling you how much momentum in one direction you transport in another direction, and D is telling you how much material or heat or sort of any other passive scalar field that you're transporting along the flow. So the end goal is to calculate these correlation functions, because those can then go into models. So and understanding this is sort of really important, and not just understanding this in one scenario, but understanding how rotation plays in, and shears and convection, magnetism, and so on. Right. So there are really a lot of things that can very fundamentally change how your turbulent fluid behaves, and you really want to understand sort of how all of these effects play into it. So you can, of course, do this by direct numerical simulation, and there's been a lot of success at that, but you really do need something a bit sort of a bit more pared down if you're going to calculate it lots of times in lots of scenarios and so on. So to that end, I've been developing this code, and it starts by just calculating the linear modes of the system. So you take as a background whatever your sort of non-fluctuating state is, and then perturb it linearly and calculate the modes you get. And you can do this very quickly, because typically that's sort of just a matrix inversion. It's a really straightforward operation. So then the key to really getting fast answers out is this linear growth and saturation model. So you assume that there are random perturbations against the background, and that these grow with the linear growth rate. And then at some point they're going to saturate. You're going to have wave crashing effects. You're going to have nonlinear interactions that sort of truncate the evolution. And you match this against a turbulent spectrum. So that sets an amplitude scale. So another way of thinking about this is that your time scale gets set by the growth rate, and your sort of distance scale gets set by the spectrum. So we take the spectrum as an input, and sort of use the results in the literature to figure out which spectrum is appropriate under what circumstances. Now there's one complication here, which is that for sheared systems, it isn't really sensible to talk about modes with a fixed wave vector, because as the system evolves, what your shear does is it rotates your wave vectors. So in effect, what's happening is that your shear bends your wave vectors in the direction of the shear, and so you need to account for that, because in many cases that's actually sort of the most significant effect. So an example is near the solar tachocline. So to handle this, what we do is sort of numeric perturbation theory. So we expand out the assumed time evolution of the mode in sort of a series, and then we term by term match this series against the growth of the wave vector. And so by doing that, you can establish a solution that's valid in a time window sort of around the time you care about. And if that window is wide enough, then sort of you can encompass an entire sort of growth saturation cycle, and then you don't need to worry about what happens afterwards. So the end result are amplitude maps like this. So what's happening here is the color shows on a log scale the amplitude of modes as a function of the orientation of the wave vector of the mode. And so then we calculate all of these stresses and diffusivities under different circumstances by summing over all of these modes and weighting them according to their amplitudes. And because this is just a numeric integration, you can really evaluate it quickly, and so you can use this in stellar and planetary contexts. So as an example of the kind of thing that you get out of this, so here I've plotted the RR, which is to say the radial diffusivity and the radial stress, as a function of rotation rate for a convecting system. So on the left is the slow rotation regime, plotted on a linear scale, and on the right is rapid rotation, plotted on a log scale. And purple is prior work for comparison. So the takeaway from this is that your stress and diffusivity really vary in similar ways, which is maybe not too surprising. You kind of would expect them to just be related by some time scale. And sort of the other important thing is that in the slow regime, things are quadratic, right? So we can actually determine that variation is expressed as a quadratic in the rotation. And by contrast, it drops off inversely as the rotation in the rapid rotation regime. And so what this tells you, for instance, is that for really rapidly rotating convection cells, you expect your convection to be inefficient. It's really bad at moving heat. And this is actually the regime that most of Jupiter is in, for instance. So this is not sort of a random extreme example. There are real systems for which this matters. So you can also calculate things like the R theta, so the polar correlation functions. So what these do is these control basically the transport of heat in non-radial directions. So this sets the angle at which you transport heat against a radial temperature gradient. And again, sort of what you see is quadratic variation in the slow rotation regime and inverse variation in the rapid rotation regime. So what this tells you is that initially your angle grows like omega squared, and then eventually it saturates as you go to faster rotation. So that kind of tells you that in Jupiter and rapidly rotating stars and so on, you should expect that in a large fraction, you're actually really not transporting heat radially. Or at the very least, you're distorting your entropy gradient so as to maintain that heat transport. So extracting these kinds of scaling relations is kind of a side benefit of developing subgrid models, because you can then apply them and quickly get these sorts of things out. Now, the same methods happen to work even if it's not convection. So you can look at stable stratification. So in stably stratified systems, you expect that the scope of the turbulence, the relevant scale, is actually bounded by the fact that you have a stratified atmosphere. And so in this case, what I've plotted are just the 6 components of the stress. And the relevant thing is that they don't all scale the same way, right? So different components are being suppressed. And this is in a sheared situation. So here you have some differential rotation, and that's the reason you have turbulence at all. So the fact that they all scale differently is telling you that they're interacting with the stratification to different degrees, right? So the ones that involve radial components scale much more rapidly because they're the ones that are much more suppressed. And as a final example, these are 2 stress components and the corresponding magnetic stresses in the case of a magnetized accretion disk. So on the horizontal, I'm plotting the magnetic field strength, sort of normalized against the various disk properties. And so that the one line is the critical MRI value. So what you see is that sort of as you go over the critical value, your hydrodynamic turbulence quenches. So you sort of rapidly drop off how much actual fluid motion you have, even as the magnetic stress continues to rise. And so that, that tells you that you continue to transport angular momentum, and you continue having a disk and so on. But the disk is no longer primarily being driven by the fluid motion. It's mostly magnetic. So I think this blend of sort of numerical integration and perturbation methods with analytic models will let us accommodate a wide range of phenomena in subgrid models that you can then use to simulate these objects on long timescales. So if you have any questions, I'm happy to take them. Yes, yeah, so we did a number of model comparisons. Unfortunately, I don't think I have the slide here. Part of the problem you run into is that the simulations don't agree terribly well with each other. But to the extent that they agree, we get similar results. So for instance, in just rotating convection, we get a pretty similar scaling law as you go to rapid convection. But we disagree about sort of the relative magnitude, say, of the radial and angular components.
Change when you compare numerical simulations and have a very small inertial range and a very large dissipation scale. If you don't include that, then I can imagine that would produce some discrepancy.
Oh, that's really interesting. So currently we just integrate all the way out to infinity, sort of using a transform to do that. We do include, there's an effect where the spectrum changes in magnetized cases at a critical wave vector. But apart from that, no, we haven't looked at whether or not changing. Yeah. Yeah, we could certainly try that. Yeah, thanks. Mm-hmm.
You also consider the helicity or helicity component for the magnet?
Oh, I see. So we don't include, say, the gradients of the magnetic field. We're just considering constant field.